Hello, lovely people. How is everyone doing today? It is a nice, cozy looking day for me, very overcast. Hope everybody else is having wonderful, enjoyable weather. Just overcast is very rarely called wonderful, enjoyable weather. Yeah, I'm quite enjoying it. Hey there, hi there, ho there. Welcome, welcome. I am excited for today. We're going to be doing my first flailing of the season. So as y'all know, today is a coding day, per the schedule. Why is my face cut off by the chat? This is not acceptable. Give me my face back, please. Look at that face. There's a face. Okay. But as y'all know, today is a coding day, and that means that we are going to be doing some flailing. Cold snap here. Happily trade sunny, windy for cold or overcast. So plan for today is we are going to do a bit of an overview, just review some of the stuff that we went over yesterday, and then we are going to be talking about 3 of the basic algorithms that became that are kind of the parents of what actually gets used in modern routing. So those are going to be breadth first search, depth first search, and of course the wonderful Dijkstra's algorithm with some discussion of the traveling salesman problem. As networking is fairly similar to the traveling salesman problem, I also found this really cool, this interesting looking blog entry from somebody who was involved from Vinton Cerf, as told by Bernard Aboba. This is published back in 1993 in the Online User's Manual. And it talks about the birth of the internet. And I think it would just kind of be interesting to read. So we may, if there's time for that, do a bit of reading today, because it's been a hot minute. We've done a lot of me talking at you, and I guess me reading is still me talking at you, but it's using other people's words. And I miss doing a little bit of anthropology. So we may do a bit of that today too. Wow, my face looks red. Maybe I'm warm. But yeah, that's the plan. That's the plan, fam. Where do we go from here? When do the trumpets cheer? There. Okay. Nope. Haha, got it. Okay. So today we are in day 2 of Routing Revelations and Explorations, and week 2 of Unraveling Network Secrets. So today is Algorithms for Navigating the Net. We're going to start off with a review from the last lesson. I'm sorry that I do not have an updated cat picture for you. Very sad, I know. She hasn't really done anything cute lately, if I'm being honest. Mostly been sleeping. It's too cold for her. Doesn't help that we had a warm spike, and her coat started shedding. So she's now even colder, but we could not ever get a sweater on her. She does deserve a head pat. Unfortunately, she tries to bite you if you give her head pats, so c'est la vie. So yeah, we're going to go over just very quickly the stuff from last lesson. Then we are going to go over what we kind of got cut off going over last session with the various kinds of casting that people can do into a network, the various different ways, the various different delivery methods people can use. And then we're going to do some algorithms. So, reminder on IPv4. IPv4 got implemented by DARPA. So it was TCP/IP was standardized as the main go-to internet protocol for the DoD back in 1980. That resulted in the DoD pouring more resources into networks that were using TCP/IP, and also resulted in other major clusters of nodes, such as NORSAR and the University College London, switching to those networks. That resulted in ARPANET switching to using TCP/IP. So that's kind of how it got rolled out to what we now have as our main internet backbone. For the backbone of our internet is built on the original lines of ARPANET, literal physical lines of ARPANET. IPv4 is a protocol. It was officially published in 1981. It is made up of a header and data, as you can see over here. So here's the header, which has particular bits of information, including a source address and destination address, so where the message is coming from and where it is going to. And this is the structure of the addresses. They're read in human numbers as 172.16.254.1. And that is the order of the IP address. There are also a certain set of reserved address blocks for particular network usage, including 10.0.0.0, and is it 0.0.0.0 are both reserved. There are a number of other ones reserved for various different specific usages. 192, thank you, that was the one I was trying to think of. 192.0.0.0 is also reserved. And those are reserved for various reasons that allow the networking protocols to work, basically. Then, with the advent of IP addresses, they needed to have some way to release blocks of IP addresses to different organizations and corporations. And so they came up with classful IP addressing, which basically said, hey, we have 3 groupings of networks. We have really big networks, which are going to be class A, which might have up to 16,777,214 hosts attached to them. We have small to medium-sized networks, which are going to be class B, which will have fewer numbers of hosts, but there can be more of these networks. And we're going to have class C, which are very itty-bitty networks. And then we have class D and class E. Class D is for a specific use case called multicasting, where you are sending to Class D is reserved for services that are using multicasting instead of unicasting. Unicasting is the standard method of sending messages out on the internet, where you are sending to one node, where you are passing your message along to one node, who will pass it along to one node, who will pass it along to one node. Multicasting is where, instead of sending to one node, you send to a bunch of nodes, who then might send to a bunch of nodes. So Class D is special use case reserved, and then Class E was reserved for future research. Clearly, we run into a problem here because not every giant network is going to have nearly 17 million hosts attached to their network. Some of them might only have 16 million, which means there's still 777,214 host addresses that are up for grabs, that are just sitting there unused. So when we started seeing just the huge number of devices we were eventually going to have to support on the internet, they realized, hey, we're going to run out of space. We did not allocate these efficiently. This scheme of distributing blocks is not going to work for us. And so they came up with CIDR, which was released in 1993. Addresses were then able to be allocated based on network prefix instead of by class, which meant that instead of having either a network prefix that was 1 byte long, so 8 bits, or 16 bits or 24 bits, you could now have varying lengths of network blocks. Varying lengths of network addressing. You could now have varying lengths of network prefixes depending on the number of hosts that you needed. So, for example, say there was still some free addressing available from one of these groups that had originally been a Class A network. Maybe you only need 2 to the 9 hosts. So your network prefix could be within that former Class A block, and the network prefix would be 23 bits long, leaving 9 bits available for you to do your host addressing. Does that make sense? So we got the introduction of this new notation to go along with this new idea. So what that looks like is you have your standard 32-bit address that gets written here, and then you have a little slash and the length of the network prefix. So that way you can see how many hosts there might be available on this network. In this case, this is a host that has a 24-bit network prefix. So this is the name of the network, 194.168.4. And then it could have 2 to the 8 different hosts connected to it, with the host identifier being here. So that's the stuff. Alrighty, and then last but not least, we have routing delivery methods. Now, as you can probably tell, these are screenshots from Wikipedia. And what I'm going to do is I'm actually going to pull up Wikipedia because it has these nice little animations, if I'm recalling correctly. And it has some good descriptions. And I would rather just use those than flub through it. So give me one moment. Would be interesting if you could buy single IP addresses like you can buy domains. Wouldn't it be? Wouldn't that be nice? I mean, you kind of can. You cannot actually be the listed owner, but if you pay for a business plan, it used to be that that's what you were doing when you paid for your internet, right? Was you said to your ISP, "Hey, I would like an IP address, please," and your provider gave you a static IP address. That is no longer the case, and we will definitely need to talk about what that means. That's part of the overall goal that we're building to, as we're talking about all of these various different network technologies, is we want to try to make it more accessible for lay people who have less technological background than me or people similar to me who have maybe been in the computer science field or been in the software engineering field or been in the network administration field for a long time. It's the fact that your internet service provider can change up your IP address on you makes it way harder for you to host your own websites, for example, which is a pain in the ass. You can say, "Hey, give me a static IP." Typically, they only have this available as a part of their business plans. But it would be nice if you could just guarantee, "No, this is my IP address. It's mine. All mine. I want it." Yeah, you can pay extra for a static IP from some providers, but if you just get a couple set ones and then take them with you like your phone number, it would be handy. 100%. I wish that was how things worked. Sadly, it is not. Let me pull up the Wikipedia article that I am wanting. God damn it. Okay. Here we are. Okay. So, there are 4 main addressing methods that are specified in the Internet Protocol. And I think what we're going to do is we're going to pull up a picture on one side of the screen, and then we are going to do the reading on the other side of the screen, which means I'm going to need another copy of this. Actually, I really liked that one, so You guys should feel special. I've been reading actual releases from IANA, which are some of the driest shit I have ever read in my life. Very informative. Really glad I did it. Oh my god. So dry. Okay. Beep, beep. Hey, I mean, what? It's best to hear it from the horse's mouth, right? Also, if any of y'all know anything about WikiWand, I am not familiar with WikiWand. I don't know if it's one of those wikis that's like scraping stuff from other sites and running independently run wikis out of business. But I really like it so far. So, cheers. Let me know if it's running independent wikis out of business. Or yeah. Anyway. So, addressing method number 1. We've got unicasting. This is the standard method of sending messages on the internet. So in a unicasting model, you are delivering a message to a single node using a one-to-one association between the sender and destination. So each destination address will uniquely identify a single receiver endpoint. So that means if we're looking over here at this lovely little diagram, this destination address will only have one IP address in it, and that IP address will belong to one host. WikiWand is just an alternative UI for Wikipedia. Excellent. Well, I like the UI. Good to know. So unicast is what we do most of the time. Next up, we've got broadcasting. This is really noisy. We don't want people to be doing this on the internet because it would flood the internet with tons and tons of packets that are not necessarily going to need to get read by anybody. Because once it's, we'll talk about why. So in the broadcast method, you are delivering a message to all nodes in the network using a one-to-all association. This is something that is very useful to do in a local network, like a local area network, but it is way too noisy to do on the public network. When you are broadcasting, you, a single node, are sending the same message to every single person that you know, every single node that you know how to connect to. A single datagram, so a packet, from one sender is routed to all possible endpoints associated with the broadcast address. The network automatically replicates datagrams as needed to reach all recipients within the scope of the broadcast, which is generally an entire network subnet. So what that's going to look like, if we jump back over to our lovely little diagram, is in this destination address, what you're probably going to have is instead of saying 172.16.24.1, if you want to broadcast it to the entire subnet of 255 hosts that are attached to 172.16.254, you're just going to do... Actually, how would it be formatted? Would it be formatted as 172.16.254 zeros? And then it's going to specify up here in one of the other header locations which that you're doing broadcast. We're going to check. The directed broadcast address for any IPv host can be taken by getting the bit complement of the subnet mask and then performing a bitwise OR. That's a complicated way to say that, but makes sense. Yeah, so you just specify it by zeroing out the areas that you don't want. No, I'm wrong. The broadcast address you specify by filling out all of the bits with ones. So .2555. And when something that has that sort of, it's a special reserved address. So when something with whole bunch of ones at the end arrives at a particular router, it sees that and knows, hey, this is a broadcast message. I'm supposed to send it to everybody who is below me in this tree. That's clever. That's the thing that I really enjoy about looking at some of these older documentation. When memory was still quite expensive and when sending stuff, basically when it was more costly to do new things on the internet or add more memory or add more bandwidth, people came up with some very clever ideas to pack more information into each of their messages. 0 and 255 are reserved for special, correct? So can't actually have 255 hosts attached to your little network. You can have 254, because if 255 is missing and 0 is missing, it's going to be 254. Yep. Oh, why'd you do that? That was rude. So this is what broadcasting looks like. Here's your little individual node. You send it out to everybody. And you let everybody know by, instead of putting 172.16, if you want to send it out to everybody who's connected to 172.16, what you're going to do is write 172.16 255, which is the equivalent of writing just a bunch of ones. I said that was clever because rather than having some sort of bit that you have to flip on or off in another section of the header, what they're saying is they've just made this special address that does the same thing. And that way, in this case, in a broadcast message, you're not going to have, in the case of a broadcast message, you're not going to have a more specific IP address to be putting into the destination field anyway, right? So either you would need to have that bit somewhere else in this header saying, hey, this is a broadcast address for all things below bit number 24, and then in addition to that, you would need to have some sort of standard way that people fill out the destination address here. But rather than having to do all of that, you instead just have that destination field contain all of that information, all of that specialized instruction. So that's why I thought it was clever. Okay. Next up, we've got multicasting. Woo! Multicasting is kind of similar to broadcasting, but instead, what happens is you are a single node, and you are delivering your message to a certain selection of nodes that have expressed interest. This is sometimes also called like a subscription model. People can subscribe to listen to you. And I want to actually dive into this and look at it more specifically. because I know what this looks like in the application layer, because it's a subscription model. IP multicast is interesting to me, though. So let's read this. IP multicast is a technique for one-to-many communication over the IP network. The destination nodes send an Internet Group Management Protocol join and leave messages. For example, in the case of IPTV, where the user changes from one TV channel to another. IP multicast scales to a larger receiver population by not requiring prior knowledge of who or how many receivers there are. Multicast uses network infrastructure efficiently by requiring the source to send a packet only once, even if it needs to be delivered to a large number of receivers. The nodes in the network take care of replicating the packet to reach multiple receivers only when necessary. Is to use multicast addressing, which is, of course, done over UDP. Beep, beep, beep. IP multicast is always available within a local subnet. Achieving IP multicast service over a wider area requires multicast routing. Many networks, including the internet, do not support multicast routing. Multicast routing functionality is available in enterprise-grade network equipment, but is typically not available until configured by a network administrator. The Internet Group Management Protocol is used to control multicast delivery. I was gonna say, definitely possible with IPv4. Maybe we just don't turn it on, but I thought we did. So let's go a little bit further down the rabbit hole, because I'm curious. Multicast routing is one of the routing protocols, and this has just taken us back to where we were. Okay. Multicast routing is a method of transmitting all subscribers registered in a group by one transmission, unlike unicast routing, which transmissions one-to-one necessary data. We've got this. We know this. You need Tier 2 service to reliably use multicast over wide area network. Gotcha. So translating that, we have Tier 1 networks, we have Tier 2 networks, we have Tier 3 networks. These are various levels of ISPs. So ISPs that are bigger and are more central to the internet backbone is going to be Tier 1. Less central, but still pretty darn a part of it is going to be Tier 2. And then more local ISPs are going to be Tier 3. The line between those various different tiers of ISPs is very, very fuzzy because a lot of it is handled in legal documentation that is private and proprietary that we do not have access to. What defines something as being a Tier 1 network is that it can send messages freely among its peers. So any network that is considered a Tier 1 network doesn't have to pay to use the bandwidth of other Tier 1 networks. How did I get here? Yes, I was translating Analog's message. So to be able to use multicast reliably, you need to have kind of that higher level of access and permissions to send things through the wide area network. Okay. Regarding IP multicast, it is a technique for one-to-many communication over an IP network. IP multicast covers some of the common multicast routing protocol. IP multicast also describes the IP multicast software. Okay, this is what I want to know. We've got A multicast routing protocol is a mechanism for constructing a loop-free, shortest path from the source host that sends data to multiple destinations that receive the data. IPv4 uses the Class D addresses. Remember how we reserved those? These ones, all here. And IPv6 multicast provides the previous feature of IPv4 and a new IPv6 feature. So IPv6 has that same address block reserved, and also allows a host to send a single data stream to a subset of all hosts concurrently. I want to know what this is. Oh no, Cisco. That's fair. Cry. Okay. Damn. I will look that up some other time. There are 4 types of well-known IPv6 multicast address ranges. We don't need to go into those details. Okay. So now what we're doing in this Wikipedia article is we're looking at these. Imagine how complicated the contract that allows you to send packets to an arbitrary number of hosts on the entire internet. Extremely complicated. Truth be told, my guess for why multicasting wound up being a thing that was specifically included in IPv4 is because we were developing DARPA was developing the TCP/IP protocol for the purpose of communicating with other parts of the United States if there was a nuclear attack. And so multicasting, the ability to multicast makes sense. The ability to send out a message to many, many nodes who might want to know, hey, California got nuked, would be useful. I think that's why we have multicasting. I do not know for certain, but given my understanding of the motivations behind the DARPA program that was responsible for TCP/IP, that just makes intuitive sense to me. Do not treat this as a factual, definite claim. Please don't. I don't have evidence for this. I don't have quotes for this. This is an extrapolation from the information I have read about this program and how the internet was developed. Okay. Multiclass tree classification. Okay, so what this is saying is there are basically 2 different ways that you can that multicasting can be implemented. So the first one is called the source-based tree, which is a protocol. It doesn't tell us how it's implemented. Cry. Apparently, it has poor scalability. Maximum delay is short between end-to-end communication. Has poor scalability. Supported protocols include these. Okay, let's look at the group shared tree. It is a core-based tree, selecting one router in the network as the root. So we've got this one thing, and transmitting information through that root router. The maximum delay in the tree is longer than SBT. The core router manages all the information, and the remaining routers manage the direction of the core and the multicast information requested by the current neighboring router. Okay, y'all. I don't know enough about multicasting to dive into how these 2 work. I am very intrigued by these, and specifically their implementations, how they could be useful in a smaller network. Oh, which is what Analog has just said. Multicast has a lot of use cases in smaller scales, but it's not accessible without building your own alternative infrastructure at this point, which makes sense. Like, you basically have to be implementing multicast for your own network of devices, which makes intuitive sense to me as to like why we have wound up in that position. Multicast seems like a very, very difficult thing to support at a large scale. So if it is a thing that you want, yeah, the internet's too big for it. The internet is too big for this. So it makes sense to me that a lot of the multicasting features have been either pushed up to the application layer with like subscriber models, or if you really want them at the network level, you have to implement them yourself. Makes sense. Because like just reading these descriptions, right? Like you're having to do, rather than using unicast modeling where you're basically just, what it's going to look like is you're going to ask the various nodes that you are connected to say, hey, how close are you to this other node? And they'll give you an answer, and then you pick the one that's shortest, probably. You can optimize for different things, but cheapest or shortest. Instead, multicasting requires you to like be making decisions about how to send to multiple different places at once, and to do that efficiently, and to do that without repeating yourself more often than you need to, which is going to be complicated as shit at a big scale. Yeah, drop packets. I would guess so. Especially because multicast would have to be UDP. Like, I don't see how you could, yeah. Doing multicast in a way that guaranteed packet delivery would be so intensive on the network. Be cool though. Anyway. If one host has a lot of problems, it eats into the entire network's bandwidth. Yep. Okay. And then we're going to talk about our final one. Sorry for going off on a little bit of a tangent there, folks. Anycast. So Anycast looks like this. It's kind of like multicasting. Anycast delivers a message to any one out of the group of nodes, typically the one nearest to the source using a one-to-one of many association. So the datagrams are where the datagrams are being routed to any single member of a group of potential receivers that are all identified by the same destination address. The routing algorithm selects the single receiver from the group that is the nearest according to some distance or cost measure. I don't think that IPv4 supports Anycasting, is what I said. Yeah, here we go. The first documented use of Anycast routing for topological load balancing of the internet-connected devices was in 1989. It was first formally documented in IETF 4 years later. It was first applied to critical infrastructure in 2001 with the Anycasting of the iRoot name server. Ooh, fancy. It can be implemented. So it can be implemented via the Border Gateway Protocol, which we are not going to dive into the implementations of the Border Gateway Protocol today, but we will be diving into them, I believe, in our next session, because the Border Gateway Protocol is the way that we decide how to send packets on the modern internet. But multiple hosts are given the same unicast IP address, and different routes to the address are announced through BGP. The routers consider these to be alternative routes to the same destination, even though they are actually routes to different destinations with the same address. Ooh, clever. As usual, routers select a route by whatever distance metric is in use. Least cost, least congested, shortest. Very cool. Oh, I didn't know that. The DNS, all internet root name servers. So anytime that you want to translate an IP address into a host name, so, or vice versa, if you have Google, for example, you want to know how to get to google.com, you got to look up its IP address via a DNS server. And all internet root name servers are implemented as clusters of hosts using Anycasting. That makes sense because you want to be able to look those up pretty darn quickly. Cool. Alrighty. And with that, we can go back to our slideshow. So we have learned about things. Okay, so first we're going to be talking about breadth first search. So I have this lovely little animation here, which apparently doesn't restart when I go backwards. But basically what happens, we're gonna just wait for it to play through. A breadth first search is meant to try to get a list of every node in a network, in a graph, to figure out the map of the graph. I can't believe I'm signing myself up for doing this. I have not written a breadth first search thing since childhood. Not childhood. Okay, so we have our root node that we are at. So we look at the node, and then we check out who it's next to. We go and visit every node that it is next to, making note of whether or not it's connected to other nodes. Then, once we've finished visiting all of the nodes that it has seen, we go back to the first node that we looked at, and we go and check out its children, and add its children to our graph. So let's get this pulled up. Okay. What was I working on in here last? Let's get my terminal pulled up. Minas Tirith, yeah! My background's Minas Tirith. It's a good background. Okay, let's get that zoomed in so y'all can see. Okay. Make dir. What I'm going to do right now is I'm going to make a directory to house all of this in, and we are going to get this uploaded, and then I'm going to make a Git repository. So, what are we going to call this? Exploring network secrets. I'm not going to call these demos because I'm writing them live. Okay. Okay. Git init. Cool. And let's make a new folder. BDS. Breadth first search. That's not what that stands for. What is BDS? For people who do not understand the command line, what I'm doing here is I'm removing recursively and forced this folder that I just made. Technically, I don't need to do this recursively because there are no files inside of it, but this is a force of habit. Your command line will yell at you if you try to just delete a directory. So RMS. Breadth first search. Why did I do that? Okay. Okay. So we now have this, which has nothing in it. And we're going to jump over to my preferred coding place and open this up. Yes, I trust the folders. So first up, we are going to make we may wind up separating this out into more files, but for now we're just gonna make a Python file, because fuck it. This is code. This is VS Code. Nice and boring, I know. I'm also regretting which folder I decided to open. Oh well. VS Code is god level freeware. Why boring? Boring not in the sense of oh, don't do that. Boring not in the sense of it's bad, boring in the sense of I know it's very basic. I'm a very, very basic bitch for using VS Code. Never been particularly happy with any of the IDEs I've ever tried. The happiest I have ever been was using a particularly customized out the wazoo copy of Vim on a friend's computer, and I never got a copy of their Vim config. And I have been searching for it ever since, or searching for that joy ever since. But I enjoy VS Code pretty well. So what are we gonna do first? Okay. So first up, we're going to look at the lovely little graphics again, unless I closed them. Okay. So here's a breadth first search. We are going to need to implement a couple different functions to be able to use this, right? You live in Tmux, so it would need to play nice with terminal. That is difficult to accomplish. I think you're going to have to stick with Vim or Emacs, unfortunately. I am so deeply regretting deciding to do this right now. Fuck. I don't even remember how to write Python. I'm panicking, y'all. Hey, Marcy, welcome to stream. No, I just want the functions. God damn it. Just give me some stump functions for an assignment, and then I'll know what to do. Here we go. Stanford assignment. We got it. Woo! Okay. Breadth first search. Common algorithm that might have been seen in a prior algorithms class. Please familiarize yourself with the function fuck. Not what I want. Any of y'all have your assignments from your first algorithms course? I don't want the solutions. I just want a list of some basic functions that would be good to implement for it. Assignments. Haha. Oh, damn. This is why I do prep before these. I'm sorry, y'all. Coding assignment. Please. Try searching pseudocode. Okay, here's what we're gonna do. I am gonna go here. I'm gonna steal the Python stump code. And delete it all. So this is from Geeks for Geeks. Okay. And then we're gonna add some additional functions that we want this to be able to do. Let's say we also want this to be able to find shortest path. Between two given vertices. What is another thing you might want to do? Some practice problems. So this will implement the breadth first search. Let's create a function to print out a depth first search. So rather than going through the level, you go all the way down through the nodes until you find a node that doesn't have a child, and then you go back up. Just want these to not yell at me right now. Okay, what are some other fun problems? Let's look up a description of Dijkstra's algorithm per our instructions here. So Dijkstra's is a particular way of finding shortest path between nodes in a weighted graph. So okay, let's do it. So I tend to start out by writing out some pseudocode for what I want this to do. So let's make watch me flail around and show that I clearly don't write a particular language these days. Python make object. Cool. I guess I should have known that because I was looking right at an object. Okay. Class. Oh, does it not like you to have multiple classes in the same thing? Def init self. Okay, so inside my node, I'm going to have the data, which Java style in Python as a Python user, you're emotionally damaged. I'm sorry. I did all of my stuff in Can you tell that I'm a fucking Python user? Pass. Okay. ID. What things do I want my node to have? Children. Also, Python file can have as many classes as you want. Cool, cool. Good. Awesome. Or let's not put children, let's put peers. Let's give it Python have an idea of like static numbers or of like a static. I'm originally a C programmer, y'all, which I know is bonkers to be saying in this day and age, but it's true. Python global variable or And if I want to make something global to just the node, will that work, or will it scream at me for defining a function or defining a variable inside the class? As a... Gotcha. Am I doing horrible things? Am I I want a way to generate node names. Generating unique IDs for objects in Python. Woohoo! Gross. These are ugly, though. And I just want something simple. Fine. Oh, good to know. Generate a random UUID. Just let it be C-like. But how am I supposed to learn, Analog? Okay. We're not using this at the moment. Am I trying to learn how to write a Python library? Not specifically. Yeah, that's what I'm using. I think you found the same Stack Overflow as I did. God, this is fucking Java. Does Python have a way to enforce type? Looks like not. No, just type hints. Typeful Python. Again, my two languages, and this is wild to say, but also object method's first argument should be self. Okay. That's dumb. Why would I have to type it out? Because the answer is that object-oriented programming got added on to Python. I don't want to do all the things. Get peers, self. Okay. Yeah, I fixed it. Once I know like a couple things, I tend to be able to switch back into whatever new language I'm using. It just takes me a bit. No, the two things that I've written the most code in is I've written very old school C. I've written C++ 98. And I've written some C++ 11 and Python for my own scripting needs, which is not object-oriented style Python at all. And then beyond that, like, so most of my school stuff was in C. Vast majority of my school stuff was in C. Very little of it was even in C++. And then professionally, I've been a React TypeScript developer. So my norms are just weird. Which is why I like to see a coding convention a style guide, and then I'm good to go. Does Python want you to use something to add to an array, or do you just do what you do in other languages where you just treat an array as a mutable thing? Array.append. Okay. Is array.append actually any more efficient, out of curiosity? What is Python? Let's go to Python GitHub. Let's look at CPython. I want to see how it's implemented. That's what I'm doing. You've done Ruby on Rails, JavaScript, and VB Script professionally. Neat. Okay, give me 1 second, y'all. Gotta sign in. My 2-factor authentication. I just did it. Okay. You've done VBE. Who needs help? We're just flailing around and having fun. Okay. Yes, take me to the array class, please. Ho ho! Oh no, this is not what I want to do. Not what I wanted to do at all. Unless array is an implementation of list, which would be weird. List is array. What I'm looking for is the specific implementation of array. Because I want to know how they do the append. I want to know if they just create a new chunk in memory or if there is actually a distinction. Okay, so there is a distinction in that if you're just manually recreating, you're not getting to take advantage of the fact that Python is actually being a little silly. It's over allocating the amount of space that is available in the array. It's not... Yes, I want the bones. I'm looking for the bones. So based on this, it sounds like what happens when you create an array is it goes ahead and just grabs a larger chunk of memory than you need. And so by appending, if you still have space in that larger chunk of memory, you're going to get the benefit of that. So basically, it's treating arrays like lists. Clever. Annoying. I want it to do what I'm telling it to do, but I'm using Python, so why would I ever assume? Okay, I think that's the basic implementation for a node that I can think of right now. We're gonna add a couple more defs. Def init self with an ID, in which case radio voice. Alrighty, folks, we are going to start with a couple more implementations of Node, simply because I think that there might be situations in which we want to construct a node that already has some predefined characteristics. So, we probably don't want them to be able to set their own ID, but we may want them to be able to set their own name so that they can name themselves silly things like, Hackerfest 2000. You can't have multiple inits? That's dumb. What if I want to have multiple constructor? Optional arguments is the method. Optional arguments is apparently what we need. How do I specify that I want an optional argument? Optional arguments in Python. classes. Alrighty, folks. Fair enough. And we're off to the races. So, let's make the snake races. Thank ya. How are we going to do this one? So, my first thought is how do we want to represent this graph? There are a couple different methods for representing graphs in code. One of them being, why are you using Python when you apparently don't like Python's assumptions? It seems to be harassing you. That's a great question. That's a great question. And one that I probably should have considered the answer to before writing in front of strangers. So there are two main ways to represent live coding. Never a good idea. But I am here to humiliate myself for your pleasure, as this is my full-time job. So, you know, and truth be told, I do think that there's some value in showing how people actually code, particularly if they're like starting to code. I'm not an amazing developer, but I'm not bad. I'm pretty mediocre. I'd say I'm middle of the road developer, and I think that it's important to show people, especially new folks, that that amount of Googling that they have to do, everybody has had to do that at some point. When you're jumping to a new language, you're going to have to look up the syntax of that particular language. Yeah, my goal is education. I think that it's really helpful to, it's kind of like doing a pair programming session, right? Like, it's showing you the thought processes that other people go through when they're trying to problem solve in the same ways that you are trying to problem solve. And I think that's really useful. It's worth showing people that they are not the only person who struggles. And if you would like to support me in that endeavor, I maybe am able to pop up my Patreon books thing. I have Patreon. It pays my bills. As do tips from y'all. ChatGPT enters chat. ChatGPT I don't think it's bad. I think that it's a useful tool for getting that stump code. But yeah, it's similar to the idea of like let me start at the beginning of this opinion. I think, yeah, it's not bad till it starts making stuff up. And ChatGPT is useful for coding in the same way that it's useful for writing, in that it can be very, very, very hard to start with a blank page. That can be very, very intimidating for people. Writing drafts, writing a first draft, writing a rough draft is, what is the quote that Watson has? Hey, Watson, are you still in chat? Beep, beep. If you're not, that's fine. I'm trying to think of that quote that you have about, that's what it is. Editing is like polishing shit into diamonds. Making a rough draft is like writing shit. And so if you have someone or you have a tool, hello, shitting marbles, something like that. Can you give me the quote? You have a great quote about drafting, rough drafts and editing. While you are doing that, I'm gonna go grab some food. I'll be right back. Did I go too fast? I think so. I think Watson might be up to things. I'm sorry. Editing is like sculpting a block of marble into a beautiful statue. Drafting is like shitting marble. Yeah. So if you can get ChatGPT to do the shitting marble part of writing a new draft or writing the first pass at the code structure you're going to need, it's going to make it that much faster and easier for you to get to the end product. You have to be careful and you have to know what you're doing. And it's similar to what you had to do in school when you were learning about... Gotcha. Sorry. Enjoy your nap. But when... That doesn't mean that it's not worth occasionally shitting marble for the learning experience, right? Like, ChatGPT is very good if what your end goal is you don't have to revisit how to do the basics. You want to get to the end product faster. So you want to skip that drafting step. But if what you're trying to do is learn and you're trying to understand the underlying concepts of how things are connected. For example, if you want to understand the intricacies of how Dijkstra's algorithm works, or understand how to build a graph, and use the process of building a graph to better understand how classes work in Python, or whatever it is that you're trying to learn, it's still valuable to do that. Same thing as it's still valuable to write first drafts for essays so that you learn how to structure an essay. Education should never be about the end result. Education should always be about the process and the incorporation of ideas, and learning how to synthesize ideas. And that's why when you're in an undergraduate computer science program, they often won't let you use libraries that implement these things for you. You have to learn how to write your own linked list, your own circular linked list. You can't just pull it in from some library that's already implemented it, because what you're learning is not how to use a linked list. You're learning the process by which one can implement efficient code. So, where are we? You know what I should have done? Should have just written it in Python. You gotta reinvent the wheel to fundamentally understand how the wheel works. Exactly. And to know what shortcuts you can take without compromising the fundamentals. You just gotta leave for work soon. Alrighty, enjoy work. You dislike the idea, why not use the tool X? Why does it exist? Then you can be proficient if you know how to use tool X, not how to write tool X. I think I disagree with you. And the reason that I disagree is I don't think that anyone's against you using tools. Right? Like, we have calculators. We have slide rules. We have computers. What the difference is your goals. Yeah, exactly. If what you are trying to do is conceptually learn how code is architected, if you are trying to learn how to write good code, one of the best things that you can do is take the easy coding problems that people started with, like, how do I implement a list? How do I make a tree? How do I figure out how to navigate a network? And try writing those out. Try to implement them. And that will give you practice with designing it. And it will help you better incorporate into your brain not only how those particular things are likely implemented under the hood, so you know their limitations better, but it will also help you get exposure to the process of writing well-structured code that you've gotten feedback on, if your teachers are able to give you feedback, if you have teachers. It's similar to, like, when you're in elementary school and they don't want you to use calculators. The reason they don't want you to use calculators is not because they don't think you should use calculators. Like, you're going to get to a point where it makes sense to skip over doing that math by hand because you know how to do it. You know how it works. What they're trying to avoid happening is having multiplication be a magical black box. They want you to understand what multiplication fundamentally is, so that if you run into a situation that requires you to have that, or actually a better example is with graphing calculators. They want you to understand how to solve linear algebra problems by yourself. They want you to be able to understand how to multiply matrices together, because there are going to be situations where you need to understand how the interior of that matrix works and fundamentally what is happening in the multiplication process in order to apply it to a real problem. Whereas, like, yeah, a graphing calculator can multiply 2 matrices easy. Sure. You'll use that. You'll use that capability. But there are situations where it's important to understand how it works so that you know how to use that process and apply it to a different subject area or apply it to a different problem set. If that makes any sense. See, Analog? Oh, we're actually getting quite... We've been going for a hot minute. I think I'm actually going to wrap stream at about... Yeah, I think I'm going to go ahead and wrap stream. But we will be back tomorrow to do fun things. Oh, yeah, tomorrow we're going to be playing Jackbox games tomorrow night. So tune in for that. It'll be fun, cool community times. And then we'll be doing some more D&D stuff on Friday. Specifically, I'm going to be working on maps, I believe is the plan. Maps and some of my beginning monster blocks for various different monsters and creatures my characters might be encountering in their first session. I also have an idea for a puzzle they're going to be getting, so we may work on coming up with riddles, which will be fun. Also, you may need the fundamentals of that process to understand something that calculators can't do. Exactly. Yeah. 100%. Anywho, have a wonderful rest of your day. I will be pushing up our code to GitHub, so I'll make sure that y'all have access to the GitHub and that I add a GitHub command here on Twitch relatively soon. But y'all have a wonderful rest of your day. And we're going to see if we have any friends who are currently streaming. Does not look like it. So we'll just call it a day. So farewell. Have a wonderful rest of your afternoon, and I'll see you tomorrow for cool community hangout times. Catch you later.